Hey, well, it's a minute after here, so let's get us started because we are going to end up being a little bit behind the syllabus here. There's just a lot of information in this. And so if I can jog your memory back to Thursday's lecture, I purposely went through those PV diagrams and did, I think, 4 examples from the end of the book there so that hopefully you would do those and be able to do the homework. The part I did not do in the chapter was what this diagram is trying to show here. And so let's wrap up this chapter. There's just one more main topic, and I'll do a few examples from it. And there's a little bit of math here. But the very last part of this chapter I did not get to. As I mentioned, I kind of stopped purposely because I knew if I did not stop, I wouldn't get a chance to do as many examples as I wanted you to see in terms of those PV diagrams and in terms of energy. So going back to the close of this chapter here, let's look at the mechanisms of how the energy is transferred, because up until this point, we really just said things like this. We said, okay, here is your system, and what we will do is we will put heat into our system, or we will take heat out of our system, or we could even have work. But what we did not explain is how is the heat getting in there? I mean, you watched me with a flame, and I put a flame on it, but there's really 3 mechanisms, and so that's the final step in this chapter. And the first one then is called conduction. Maybe thermal conduction is more appropriate because I'm not talking about electricity and electrical conduction, but thermal conduction. It's the easiest one, I think, to understand conceptually, and certainly the one that gives us some mathematical tools. And so let's spend the majority of this, hopefully it won't be quite a whole hour, but you know how much I like to talk here. But hopefully we can wrap it up here. But let's do conduction here. And it probably doesn't surprise you if you take something hot and you put something cold and you put them next to each other. On a molecular level, if we said something was hot, what do we mean about the molecules?
Moving fast.
Yeah, they're moving fast. What about the cold side? Moving slow. Until you put them together, what happens? Yeah, so the fast-moving ones collide into the slow-moving ones, making them go a little bit faster. I'll put a little arrowhead over here saying hot to cold, but I don't mean molecules are going hot to cold, and that's what I want to emphasize. This is what we call conduction. There is a flow of energy. We called that heat. We labeled it as Q. There is a movement of energy from one object, so we'll call that the environment, to the one of interest, our system. Or perhaps it is out of the system and into the environment. There's a lot of different ways we could apply our first law of thermodynamics here. But nonetheless, there is a flow. This is called conduction. And we can put some numbers here and some ideas. And that's what this picture is here. And so this picture is saying, what if you have an outside that is hot and an inside that is cold? Maybe this is, say, the kitchen. This is, say, inside the refrigerator. Or I guess it could be just as well be outside on a summer day and inside the house, or the reverse, inside on a winter day and outside. But we have 2 temperature ranges, and we got something insulating it. And what's going to happen is this. Molecules here are going to hit here, hit here, hit here, hit here, hit here, hit here, and hit here. So there is going to be a flow of energy. Energy is going to flow. And the question might be, at what rate does it flow? And so your author, without much proof but kind of a small discussion, says, then how quickly would these things flow? And so that's why he puts up this diagram here, and he says Q per time, dq dt. the rate at which energy is flowing. Now, let me also make this pretty clear. We are not talking about the initial setting up of this. This is after a long period of time, because when you first set it up and you put, say, let's just say this insulating material, they don't really say what it is, but for this room, let's say it's this block wall of concrete. So we have a hot, well, today's a bad example. It's not even really hot or cold outside. But if it was hot outside and cool inside, then we could have a block wall between them. And what would happen, of course, this edge of the block wall would be about the same temperature as the outside. This edge of the block wall would be about the same as the room. And so there would be a temperature gradient, a change in temperature going from the hot to the cold. But everything in this wall, although it's at a different temperature, stays at that temperature. And that's what I'm trying to emphasize. And so I'm not talking about the first part. The first part would be heat would flow in and warm that up. That's where the energy would go. But once this whole insulating material warms up and has a temperature gradient, then the energy is flowing, and whatever flows in here flows by here and flows out here. There's no absorption of energy. The temperature is not going up. Am I making sense? So this is what we call a steady state equilibrium. And so this is what that means. I think your author uses the symbol P for power, right? Energy per time. Now this is a thermal energy, not like we did in Physics 21 where it was mechanical energy and we were looking at the work done per time. This is the Q per time. This is the flow of energy. At what rate does energy flow through this wall? So again, if this is a hot outside and the concrete wall and then the cool room, we would want to know at what rate is energy coming into the room. Because obviously to keep the room cold then, we would have to build an air conditioning system that would take energy out of the room at that rate. Otherwise the room would start to warm up. And so the better we insulate the room, the smaller the air conditioning unit, or the less work the air conditioning unit has to be. The poorer the insulation, then the more the air conditioning system has to work. And your author, again, without much proof but a little bit of discussion, says that rate would be equal to what? And one of the first things I think is the obvious piece is the change in temperature. What is the rate of temperature change? What is the high temperature minus the cold temperature? So hot to cold. What is that temperature gradient? Because if there is only one more degree warmer outside than inside, there's not a big incentive, if you will, for the energy to flow. If it's 2 degrees, well, the molecules are moving a little bit faster. And so it's the difference between those two determines the rate at which it flows. Another one that is hopefully obvious is how long is this? In that place they put L. It's inversely proportional to how long it is. You could imagine that as the energy tries to flow through this, something that is twice as long is then going to be twice as hard for the energy to get through there. Another little factor the author puts, and I don't think he really represents it in that picture in any way, so maybe I'll spell this one out. This is the area. It would be the cross-sectional area. Like I said, that's a two-dimensional picture, but if this was my insulating material, this was the wall, the sheathing on the wall then this is the hot side, and this being the cold side, then the length is the thickness of the wood, but the area is this whole area of wood. It's got to flow this way. Of course, if I used it in this fashion, then the heat would have to go through a much smaller area, and it's harder to get through there. So you can imagine that twice the area would make twice the energy flowing. 3 times the area would be 3 times the flow of energy. Then those are the big factors. And so what is the temperature difference? How long or distance does it have to flow? And then through what area can the energy flow through? And the last piece of this puzzle is the K And I guess I should put absolute value because, yeah, I'm just going to put absolute value because it'll go from high temperature to low temperature. So I guess without absolute value, I'd need a negative sign there. But I think your author does a absolute value. So I'll put a positive sign there. But this would be the proportionality constant. This would say something about the material. And so these are the 4 factors that would determine how it flows. We're going to call this then the thermal conduction constant. And you could imagine that each material would have a different thermal conductivity. At what rate does one molecule bump into another, bump into another, bump into another, so forth and so on. And so again, we see these 4 important pieces. What's the temperature difference between the 2 sides? How much length is the energy trying to transfer to? The area it has to flow through. And then the material. What is the material made out of? In fact, that leads me to kind of my first little demo here. This is what we call a conduction meter. It measures the rate at which energy conducts. If you look closely at it, it is a hub, if you will, and it's got metal rods sticking off the end. There's 5 of them. Actually, there was 6, but the aluminum one melted. Got too hot. All right. So there is a copper, a brass, a nickel, an iron, and a stainless steel. And if I put the flame right in the hub, and what I essentially am doing is warming up one end of each of these 5 rods, the end that is near the hub. But as the end of the rod gets warm, it will hopefully then conduct that heat to the other end of the rod. Now you might have noticed the end of the rod have little red pieces on them. Oops, talked too much. But those little red pieces are wax. And so did you notice the first one fell off? And the wax got hot, the wax melted. And so the wax is an indication of the rate at which the energy is going to flow down. And so it came off that one first, which was copper. Then we've got nickel. No, that was, sorry, brass. This is nickel, this is iron, and this is stainless steel. And so each of them will conduct the energy down, but some faster than others. And this one is set up so that the copper is the fastest. The aluminum would have been next, but it's gone. So then we had the brass. I think the iron and nickel, yeah, there goes the iron. Nickel should right behind it. They're almost the same. Yeah, there goes the nickel. And stainless steel will be here till Christmas, so I'll leave that alone there. And it just takes a long time for that one. But they all have their own set of numbers. And in fact, if we kind of look at table number 3 in your book on this chapter, they list all of these. And they say, okay, at what rate do they flow? And so you can see up here that one of the highest values is copper. There it is, in watts per meter per degree Celsius. And so as we put this in, we would have to put in that number. And so copper is a big one. Now it's not quite as big as silver, so if we had a rod of silver, I guess it would be even faster than the copper. I can't afford the silver, so we just do the copper. And so copper is used a lot for just those reasons. It's not as well as silver, but it's pretty good. And then you can see on down the list, here's the iron. They don't have stainless steel in there, but it would be even less than the iron. And there's the aluminum, which I didn't have. So they don't have the same materials I have. But my point is, you can see that every material is going to conduct. But every material is going to conduct at a different rate. That's the key here. And so this number varies. And so the conduction rate depends on 4 factors. And of course, a big one is the material. Oh, a couple questions, yeah.
Is diamond conductive?
Oh, diamond is an excellent thermal conductor. Now, I'm not saying electrical conduction. Don't mix the two. It does not conduct electricity, but it's an excellent thermal conductor.
Well,
yes.
Because conduction is technically the movement of the molecule.
One pushing on the next, right.
And electrical conduction is the movement of the electrons.
Electrons, right.
So what's the difference?
You just said it. One is the movement. Okay, so if I were to have an atom shake, a whole atom shake, how well does it shake the next one? Things that are really hard, like diamond, can do that quite well. This one moves a little, makes that one move right away on down the line. And so diamond can conduct heat very, very well. Electrical conduction is the actual movement of the electrons. So the electron has to actually leave an atom and go to the next and go to... So that's a little different mechanism. Although, don't get me wrong, they can easily get hooked together because things that are good electrical conductors can also be very good thermal conductors, because this electron, as it moves, can actually then get, an atom can be moving, push, and there's an electrical force that pushes the electron. That electrical force pushes the next atom. And so the fact that the electron moves helps the movement of one atom influence the movement of another atom. So electrical conductors are often very good thermal conductors also. They don't necessarily have to be. In fact, that's the world you guys are going into. Materials such as could we ever have ceramics or polymers that are really good electrical conductors, but really bad thermal conductors. This would open up a whole new world of material science. Yeah. And diamond's the reverse of this. Diamond is something that's a good thermal conductor and not a good electrical conductor.
Is there a hard and fast line between a good conductor and
no, and so like all of these, we say conductor, we say insulator. The truth is, it's a whole spectrum, and we put numbers in them, and we say, all right, and so usually everybody says, oh, the metals are all conductors. Well, okay, but everything conducts. It just, the metals tend to be a lot higher than these other things. And so people say, well, rubber here is an insulator. Well, it does conduct, but look at that number compared to, say, copper. It's really, really, really small, and a huge difference between them. So, using the word conductor and insulator is more of a human thing. We're just trying to give a general description of, oh yeah, heat flows really well, or heat doesn't flow really well. But better for us is the numbers. How well is it a conductor? Or how poor is it a conductor? So anyways, you saw that. And since I didn't have any aluminum, I thought I would show you this one, because here's a fun one to do. Here is a piece of aluminum. It was missing here. But to show you how well aluminum conducts, let me put this aluminum piece right here. And as a comparison, I'll put a wood piece right next to it. And I thought, just for the heck of it, I got a little stainless steel piece right here. And so what if I took a small beaker packed with ice and put it on wood? Well, it's going to melt, right? Heat is going to flow into that. Now, some would come from the room, but some would come from the wood. Forget the room for just a moment. Let's just look at the wood. The wood would conduct in. Well, the wood down here has a pretty small conduction rate compared to aluminum. Aluminum up there is 238. Maybe I'll get it closer so you can see. Here's that same chunk of ice on a piece of aluminum. Can you see a difference? And hopefully you can see the flowing of heat out of that piece of aluminum into the ice and melting that ice right before your eyes. And I think it's a good experiment that is just impressive how fast aluminum can conduct and how slowly wood and stainless steel conduct compared to that aluminum. In fact, it kind of reminds me of one of those infomercials like, hey, you want to de-thaw your chicken? Take your frozen chicken, put it on this magical platter, which is just a piece of aluminum, and kind of expensive piece of aluminum for 20 bucks. You can give me a piece of aluminum. I can get a chunk of aluminum for $1.50. Why do I got to pay 20 bucks for a piece of aluminum? But nonetheless, they'll give you a chunk of aluminum for 20 bucks and it will defrost your chicken very, very quickly because they are having you put it on the aluminum, not the stainless steel, and certainly not in the refrigerator, although I guess that's what you're supposed to do, thaw it in the refrigerator, right? So that it doesn't grow bacteria and you get sick. So don't take my word for it. Don't do it on the outside of the refrigerator. Do it on the inside of the refrigerator. But
That's the copper when it's a lot faster.
yes, I think copper is a little bit faster. Yeah, yeah. Yeah, and silver too, yeah, yeah. And so it's amazing how quickly it is, right? I think it's quite impressive, and so those are kind of neat to see. But let me point out a couple other things in here. Of course, it doesn't just depend upon the material. Doesn't it also depend upon area and length, right? How much you're trying to. All right, here's why I say that. Because if I were to do something like this, a piece of paper, here's a piece of paper wrapped around iron. Here's a piece of paper wrapped around wood. Probably doesn't surprise too many of you that if I were to put a piece of paper in the fire, it catches on fire and burns. Not a surprise, is it? I take a piece of paper, I wrap it around metal, I put it in the flame, I put it in the same flame, and it's supposed to burn, right? It's paper. How come it doesn't burn? Yeah, the metal is a good conductor, and so the energy is going into the paper, but before the paper can warm up, it flows out of the paper and into the metal. And so this piece of metal is beginning to get warm in my hand, but it's not warm yet. And so as it is warming up, it is really essentially keeping the paper from getting too hot. Looks like it started to get there near the end, and its thermal conduction was actually very important in what was behind it. And so you might have noticed this on a different scale. If you were barefoot this morning and you stepped on carpet, it might have felt warm. If you stepped on tile, it might have felt cold. Was the tile really colder than the carpet? No, they were both there in the house. It was both, whatever, 52 degrees. Well, maybe it wasn't that cold. Hopefully it wasn't that cold in your house, but 60 degrees in your house this morning. But why would the tile feel colder? Yeah, it conducts it away. So the carpet, when you put your foot down on carpet, the heat from your foot goes into the carpet and then it stays there. And so the carpet really is now warm under your foot. But when you step on the tile, what happens? Yeah, the heat goes out of your foot to the tile, flows away, and you still have a piece of cold tile under your foot. So more heat comes out and flows away. And you still have a cold piece of tile, and it flows away, and it flows away, and it flows away. And so the effect you feel is not that it's cold, it's that you keep feeling the energy flowing out of your foot. And you call that cold, but it's not. It's the cold you're feeling. It's not that the temperature was any different. It's more that the temperature stayed cold, and the carpet then quickly warmed up. And that's what's happening here with this paper. It is just flowing through the paper. Now, granted, paper does not have a very large... Do they have paper on here? Well, I'll take it as wood, but it does not conduct heat very well unless... How can I make this a pretty big number? Okay, pretty big area, so you can see I have a big wide piece of paper. And what else? And this is what I was taking advantage of. That paper is literally paper thin, right? And so I can take that paper and roll it real tight, and the thinness of it allows it to conduct pretty well. And so sure enough, it does. And it, conducted it away. In fact, let's try another fun experiment before we get into the second mechanism. But if I take a paper cup, fill it with water, can I boil water in a paper cup? And again, just like that one you just saw, it's surprising, but you can boil water in a paper cup. What hopefully is happening right now is something that has conduction, but it goes to the next step. It also has convection. And so the second mechanism will show up here after we have our conduction. We will have our convection. And so what I mean by convection is simply this. And maybe I'll draw a picture here, but I'll put the word convection on here. Maybe I should also do conduction, because this is part conduction, but then leading into convection. Because what we have is we have this paper cup. We filled it with water. We put a flame underneath it. And as we were talking about earlier, this paper cup is very, very thin. And I guess I erased it here. Maybe I'll put it back. But the rate of flow, depending on the material, the area, the temperature difference, and the thickness of it. And in this case, that is a small number. And so the energy can flow actually kind of quickly through here, even though it is paper. Ah, good. It's boiling already. That was faster than I expected. Okay, good. But yes, you can boil water in a paper cup here. And so what ends up happening is Q flows in, right? Heat flows in. And that part is the conduction. And then, of course, it gets to the water molecules. And then something else quite interesting happens. What happens to water molecules when they get hot? What happens to anything when they get hot? Okay, they warm up. They go a little bit faster. We called this in the last chapter thermal expansion. So let's put thermal expansion together with Archimedes' principle. If you remember, Archimedes' principle was things that are less dense end up floating. All right, so if you have some water, in this case water at the bottom of the cup, and you warm it up, what's going to happen? It's going to expand and it's going to rise. If we put thermal expansion with Archimedes, we get that phrase, warm water, warm air rises. And so what will happen then is this will rise. And so what begins to happen is anything that is warm, or in this case hot, rises. And then of course, if that's going to rise, what else happens? The cool water is going to sink into its place. And that's what keeps then the whole thing stirring around, and that's what transfers the energy actually quite quickly, because now the top is going to get warm even though the flame is down here. Notice we did not have to conduct the heat all the way to the top. We conducted the heat through the paper. Then the hot air rose to the top, and then that was our convection. And so that's what convection is. Convection is these movement of the molecules from point A to point B. And so in your mind, this will, I think, help you realize the difference between conduction and convection. Conduction, the molecules didn't move, right? I just put hot object next to cold object. if this was an aluminum piece next to a brass piece. If the aluminum is hot, then the molecules of the aluminum are here and they stay over here, even though they eventually make the brass molecules start to go faster, right? And so these do not actually move in conduction, but in convection they do. And if you've ever got on up to change a light bulb, let's say, or to dust a ceiling fan, as we all do that so often. Oops. We, go up to dust our ceiling fan. But if you stand up there, you will feel how warm it is, because what happens to all the warm air in this room? Yeah, it rises up. That's why many people in their house will take and put a ceiling fan. And many people think, oh, a ceiling fan, that's great for the summer. No, it's also great for the winter, because where's the warm air? Yeah, up at top. And so you often have a switch on your ceiling fan, because when you draw the air up and run the ceiling fan in reverse, it will force the warm air down and along the cool walls of your house and then stir it around. And so we can take some of that energy that we've got up there and stir it around down here. And that can help dramatically in keeping heating costs low, because you're not trying to heat it so hot up there that you're comfortable down here. Of course, in the summer, then you kind of switch the fan the other direction so that it actually blows on you. And then we're back to our last chapter where you got your evaporational cooling. You want the air to blow on you and to be cooling you down. And so that's an important idea. Did I see a question? Yeah.
Are the thermal conductivity constant and heat capacitance inversely proportional?
No. Remember, those are really two different things. This number is the rate once it has already reached what that word I used, steady state. In other words, if the energy is flowing in, Q, the first thing that has to happen is we have to warm this end of the metal bar. How long that would take would depend upon what you said, the specific heat. Okay, so that may take a while. Fair enough. And that's a matter of how much energy it has to warm up. But once it gets warmed up, then specific heat is not an issue anymore. We're not increasing the temperature. We're not putting energy into the metal to warm it up. It's already been warmed up. All we're doing now is letting the energy transfer from one molecule to another, to another, to another. There's no more net gain. That makes sense? So there's no connection then between the rate of the conduction and the specific heat of it. Now there would be a connection piece by piece, but there's not a general rule we can say about that. Your author took this opportunity to show you an old-fashioned radiator heater here, and said, let's look at heating a room here in 15, and here is an old radiator heater, which basically it gets hot. Usually a steam comes into the pipe and the hot steam warms it, or it could be a hot oil. But if this area gets hot, what happens to the air right here? It rises, right? And without any kind of fan, it should circulate around the room in the sense that it gets hot, brings in some cool air. This air gets a little cooler now and then more hot air, and so it keeps pushing it around the room. And so it uses kind of a natural process convection is the natural process to circulate the air around and to get the whole room warm. You probably see that in your water heaters really well. If you have a water heater, you'll have something in the garage or outside on the wall or in a closet where there's a flame underneath it. And a lot like this one, you warm the water, but the water that warms first is the stuff at the bottom. Then where does it go? Up to the top. And so in the morning, you probably have something like this in the water heater, where you have the hottest water in the water heater up at the top, and the stuff in the middle and at the bottom aren't quite as warm. They're probably still very warm, but not as warm. So when you turn on the shower, the pipes draw the water right off the top here, and sure enough, it is hot. If the plumbing is built well, the cooler water will come in with a long pipe down the center and let new water come out. So as you take the water off for your shower, cool water will come in. It will come in near the bottom. It will stay at the bottom, again, because of convection. And that's where the flame is. And, of course, it will start to go up. Kind of depends on how much hot water you're drawing. Usually in a shower, it's quite a bit. So the cold water begins to go up, maybe up to there. The little flame under here is desperately trying to warm it, but it can't warm it fast enough. And so the cold water is coming up. And maybe about partway through the shower, you would notice this warm water has now gotten up to here. And so you probably notice the shower's not as hot as it was when you first got started. It's still nice and warm. You might even turn the dial a little bit and say, you know what, I'm going to just go a little more hot water, or turn down the cold water a little bit. And if you took a really long shower, eventually you would realize that, oh, now the cold water is getting to me, and you have nothing but cold water there. And so there's our natural convection currents. Uh-oh. Did I let this finish? Well, I guess I did. But there's the water. And so the water definitely will boil in a paper cup. And I guess I didn't put any numbers in there, but water boils, 212 degrees Fahrenheit, and paper burns at 451, at least according to Ray Bradbury, right? And so paper burns at 451. So as long as we had boiling water in there, 212, it kept it cool. But as soon as that was gone, it quickly went up to 451 and caught on fire. Yeah.
It looked like it started burning from the top down.
Probably did, because again, I've got bubbling, boiling water there. And when it was at least halfway full, it probably was going all the way to the top and keeping the top cool. But as we got down to just the skimpy stuff at the bottom, it was kind of just left the top part bare without any water to cool it. Yeah, yeah. Anyway, so there's our standard conventions. Of course, I can't, really complete this section without a mention of where we live, because Santa Barbara, our convection currents are awesome, and that's why we pay a huge financial price to live in Santa Barbara. We rent a one-bedroom apartment for $4,000 a month or some ridiculous thing. All right, I'm exaggerating there, because I guess I don't know. What is a one-bedroom apartment? Like $2,000 a month? 1,400? 1,500? Okay. Anyways, but one of the nice things about coastal Southern California, and particularly Santa Barbara, is exactly this, that if you take the ocean here and you put a city, I'll put Santa Barbara here, and we put some San Ynez Mountains and maybe San Ynez Valley, and then we'll put bigger mountains out here, but the sun comes up, and particularly in the summer, the rays of light come down. Some of them are hitting the ocean. Some of them are hitting the inland valleys. This being rock and sand warms up. It has a lower specific heat. If we go back a chapter, then the water, if you remember, water has a large specific heat. And so what will end up happening is the ground here will start to get hot. The ocean will not. Once the ground gets hot, the air above it gets hot by conduction. Then convection is going to make that air rise. If that air rises, what happens? It's going to blow in some cool air to replace it. And so we call this the summer breeze, the afternoon breeze. You get up in the morning, And there's absolutely no wind. I mean, you can just, light a match, blow it out, and the smoke goes straight up. That's at 8 a.m. At 3 p.m., it looks like the flag on the flagpole is just going to tear in half. The wind's just coming in. It's not like a strong wind. You wouldn't call it a storm or a hurricane in that. But that flag is in full mast. It's just flapping back and forth. And what has happened is the inland valleys have started to get hot. The convection currents are rising. The wind now is blowing over the ocean. The other nice advantage here is the high specific heat keeps the ocean cool, and that makes the air cool. And so sure enough, we get a cool afternoon breeze. And so it would have gotten hot, but what I call Mother Nature's air conditioner kicked on. The reverse can happen at night, because this can cool down, and if this gets cold, then the air can sink. The air can sink, and as it sinks, it will blow from the inland and out to sea. In this area, we call them sundowners. We say, about an hour after sunset, every day in the summer, we get the winds. We get in the opposite direction. And in the canyons and passes, this could be enormous. One of the worst nights I spent was in Gaviota Pass there when January evening, the sun went down and the wind blew and blew and blew, and it was like 60 miles an hour. I thought it was going to blow my whole trailer over here. It was just like, I spent the whole night going, okay, let's get out of this machine here and before we go over. But it can really blow. And then again, there are all those convection currents. And in fact, I brought this out for the BBs, but I also grabbed this stuff. You might recognize this. Here's a power supply. What do you notice on this machine right away? Oh, how am I doing on time? This heat sink. It's made out of an aluminum. Here's some ones that we have removed so you can see them a little bit better. But the idea here is as this works, as we turn it on and plug it in, there's going to be heat from our electronics. How do we get the heat out? Well, the first thing is conduction. We've mounted everything to aluminum, and the aluminum will conduct out. And so these fins get warm by conduction. Then what happens to the air between the fins? Yeah, they get hot, and then it rises. And so as it rises, then cool air comes in. And so we don't need to put a fan on here to blow it. We just have it mounted something like this. And notice they're not mounted like this. Right? That would block the flow of air because the natural convection current is for it to rise. I thought it might be fun to actually observe the rise. So I've got hot water. Well, it's not hot yet. It's just red. But if I take and I fill this with hot water, and a second one with hot water, you will hopefully notice a huge difference in the transfer rate between these two experiments. Because these other two are clear and they're cold. If I put hot water on top of cold water, nothing much happens. Hot water already has risen. It's already at the top. Hot water stays up there. Cold water stays down here. This is going to stay hot and cold for a long period of time. But what would happen if I put hot water on the bottom? What's going to happen to that hot water? Yeah, it's going to rise, right? And as it rises, you can kind of see the color change. It kind of looks a pink, if you will. And this is getting warm. And of course, this is going from hot down to warm. And so this is getting more pink, and this is getting more pink. And so again, there's a difference in the rate at which energy is transferred here because of our convections. And so that's a big second mechanism of how energy is transferred. And then finally, the third way, which is a little difficult to explain at this point. I'm glad your author includes it because it would not be a complete chapter without it. But I'm also glad, and I'm going to say the same thing, that he says it has nothing to do with movement of molecules or atoms. And so it is a little of a misfit for this chapter in the sense that we can't really talk too much about it. We will do more of it when we get to, I guess it's chapter 40. But we like to say mechanism number 3 is what we call radiation. Maybe I'll spell this one out, but here heat then is transferred by, oh, and here's going to be a fancy set, electromagnetic waves. Ooh, what are those? Well, one example of electromagnetic waves are light waves. And that's where actually our next unit will be. So when we're done with our thermodynamics and then done with spring break, we'll start with our optics. But electromagnetic waves, light is probably the best example I can give for those of you who haven't gone through Physics 122 yet. I'm afraid that the word radiation kind of scares people for a moment, and so I don't mean the radiation kind that causes cancer, all right? But have you ever stood in front of a fire and felt the warmth? What are you feeling? That's a radiation, well, it's a radiation cooling on the fire's point of view. It's a radiation warming for you because you're being hit by what we would call an infrared radiation. The sun is another example, is it gives off this radiation. We would call it sunlight, but it warms up the planet Earth by sending 93 million miles away radiation. Between the sun and the Earth, there are no molecules. So does the sun warm up the Earth by conduction? By convection? But by number 3 here, radiation. And so there is a push, if you will, of these waves. And so if I take an object such as the sun or a fire, I'll draw these waves. But like I said, it's a little difficult to kind of discuss this because it doesn't have anything to do with molecules. But it is an important one. Obviously, the Earth would not warm without it. And so the energy coming to our planet Earth is crucial, and it's based upon this radiation. A fire, both of those you're familiar with, and you probably have felt the thermal radiation coming from it. But here's where I want to extend that. What if it's something not quite as hot as a fire? What if it is just this book sitting right next to me? Does it radiate? And surprisingly enough, the answer is yes. What we will soon learn here is that whether something is hot enough to be what we would call on fire or cool enough to be at room, it's just a matter of how fast the molecules are moving. And so these have molecules that are moving, and this is giving off radiation. There is radiation coming from this book to me. It's a thermal radiation.
You just answered.
Okay, and so I can't see it with my eyes. Maybe you've seen some of those thermal imaging pictures where they'll take, like, if all the lights were off in this room so there was no visible light, every human body in here would be at a warmer temperature than, say, the desks and the chairs, and so they would be giving off their own unique set of radiation, their own set of colors. And so if we took a thermal imaging of this room, we could say, okay, there's a student here, and it would have an outline of your body. Where is the energy coming from? And so to illustrate this, Stefan did a couple of experiments. And he came up with a couple of neat formulas, which we'll show you. But I'll start it by saying, take a look at this experiment. Stefan said, okay, if I were to take two objects that are almost identical, they're the same size, the same density, almost the same material, except one is a shiny and one is a black. And right now I don't have anything in there, but I'm going to put water them in a second. I bet you would be surprised if I took a spotlight and I were to shine it on here. Do you think they would warm up at the same rate? No, why not?
Because one will reflect and the other will reflect.
Right, it's a radiation issue. It's a transfer of energy by electromagnetic waves. You probably experience this more with a t-shirt in the sunlight. If you go outside on a bright sunny day in a black t-shirt, well, what happens? You tend to get pretty hot because the sunlight gets absorbed on that black t-shirt and stays there. But if it's a white t-shirt, what happens? It reflects off. Well, the same thing here. If I were to take a big giant spotlight on here, this would absorb a lot of energy. This would reflect. And so you're going to watch this one warm up. In fact, that one's probably so obvious that I didn't bother to set up that experiment. I wanted to try the opposite. And so I'm going to take these thermometers out and fill these with hot water. And so I will first kind of what I call pre-warm them. And so I got some hot water, okay. That will warm up the tubes. Okay. So my tubes are already pretty warm. That cooled the water down a little bit, so let me do the same thing again. And this will be my attempt to get them about the same temperature, but it's not easy to get them the same temperature. It never comes out quite the same, but I'm going to try it nonetheless. I spilt a little bit on the outside. Not good, because that gets evaporation on it and cooling. All right, but I'm going to go ahead and start these guys with my thermometers, which actually they don't look like they're calibrated the same. Or maybe this one's closer to that. Oh, maybe that's it. But if I put it in the black one and put it in the silver one, they're roughly the same temperature. Let's change it. Okay. In fact, they differ by a half a degree. But are they going to cool at the same rate? See, they didn't warm at the same rate when we talk about a spotlight. What about cooling? Will they cool at the same rate? Which one will cool faster? And the dark one will cool faster. And why? Good, I'm glad I picked this one. Let me go back. Now, let's go back. If I was warming them from the outside, if I had put cold water in there and a giant spotlight, which one would warm faster? The black one. And why? Because it would absorb it. Or in other words, the silver one is reflecting it away, right? So now, keep this in mind, and this I think is the hard part, is where is the hot object? Inside. Like this book, it is radiating. So imagine me inside, and I go to radiate out. What happens when I hit the silver lining? I bounce back in. I get reflected back in. The heat gets trapped inside. What if I hit the black lining? It gets absorbed. And so the radiation goes out. It would hit the black lining. it would get absorbed, so the black edge would get warm, but then the convection currents in this room would cool the black edge. And so
the water's not giving off any light?
the water is giving off light. It's giving off radiation. And that's the point I'm trying to make. And I got to admit, the hard part, because if I were to take a spotlight and put it on here, you would say the spotlight is giving off light. Fair enough? Because you can see it with your eyes. And my point is, there is a lot more, even though we haven't discussed it yet, although those of you who had 122 will, and we'll get more into this in the optics, there's a lot more to the electromagnetic spectrum and a lot more electromagnetic waves than just what the human eye can see. There is what we call thermal radiation. There's what we call the infrared.
And black absorbs them all.
And black, well, we got to be careful when you say black, because usually when someone says black, they mean black because it absorbs all the visible light. The real question is that also black in the infrared? And they usually are. This one is. So it's black in the visible, but it's also black in the infrared. And so if I've done this right, I should be getting the black one to cool. Yeah, and it is 64 to 67. And so the black one cools at a faster rate. Yeah.
Does it make a difference if you have your coffee inside a black mug or a white mug?
Oh yeah, because the black one is going to cool faster. Look at some of these thermoses. What color are they? Yeah, they are shiny. They're trying to trap that heat back inside. The real good thermos, a really good thermos, will often be made something to this effect. It will have an inner chamber, and if you look down inside of it, that inner chamber will be very shiny. And the idea is when you put hot inside of there, it will, try to cool down by this radiation, but it's going to get reflected back on itself. And it won't be able to cool by radiation. Also, the walls would want to reduce transferring of energy by conduction. And so some thermoses use kind of a styrofoam in between them. What would be even better than that? A vacuum, right? And so some of these are then evacuated, closed off and evacuated so there's no molecules. Because how much conduction are you going to have with no molecules? Nothing. You can't have conduction, you can't have convection. And so the vacuum is really nice. Although, you often have to make it a little bit thick because you make it a vacuum, then there's no molecules in there, and the molecules on the outside create a lot of pressure, and they want to smash that thing. So then you got to make it thick. And if you're making it thick, then those are molecules, and then that conducts. So the question is, do you make it thick out of glass? Does that work better than making it thin glass with styrofoam? But you can. There's a really expensive thermos will keep your coffee hot all day long, even if you left it out into the snow. And some of these construction workers, like in New York, that's what they'll do, right? They'll put their hot drink in the thermos. They'll head off to work at 6 a.m. They'll go on the construction site. They'll put their little lunch pail out there and next to the snow, and it'll just sit there till lunchtime. 6 hours later, they'll open it up and still got their hot chocolate or hot coffee, and even though it's been sitting out in the snow, and so it's really thick. Well, like I said, this one I think I have a little trouble talking about it at this point because it has nothing to do with molecules, and it's hard to discuss. So we're going to come back to it, but some experiments were done by a guy named Stefan. So he measured this. He measured how much energy comes from this. And he was able to figure out then that there would be some constant based upon the area. And he found out that it depended upon the temperature to the fourth power. And this is measured on the Kelvin scale. And so you can imagine then that the amount of energy coming from something really increases dramatically as its temperature goes up. Again, that's why you and most of us probably look at something like hot water and we put our hands on it and say, I don't feel anything coming from this. This is not at all like a fire. When I put my hand out near a fire, I can feel enough energy that it registers on my nerve endings, and I say there is energy flowing from it. But when I do that to hot water, I just don't get that same radiation effect. Now, if I touch it, then it's hot. There's a conduction that goes on, and I know it's really hot, but I just don't feel the radiation coming from it. But if you increase the temperature just a little bit, the amount of power goes out dramatically, and so sure enough, by the time it gets to visible light, you put your hand out near a fire and you go, oh yeah, there's plenty of radiation there. And you put it out to the sun, you go, oh yeah, there's plenty coming from there. So it can change dramatically. Yeah. So this is, and so this is temperature to a fourth power. And that's the first one I wanted to mention. Another one that maybe is obvious is the area. Obviously, the energy is coming from the surface area. So the more surface area, the more it's going to radiate. That kind of makes sense. But these other two I will mention. The E is the emisticity of it. Emistivity of it. It's a number that is labeled from 0 to 1. Emissivity? What? Emissivity. Emissivity.
Emissivity is what you say.
Emissivity. Okay, that's how it's spelled, I'm pretty sure. I can't say it. All right. E. But it is not the natural exponent that you were thinking. It is a number right here that would make a difference between something black and something silver. Okay, if it either absorbs or radiates really well, we would give it the number 1. And so this number 1 is for something that is black. The number 0 is something that would reflect perfectly. That would be either a white or a shiny reflection. And again, we're not going to do much with that. We're just putting some numbers in here to give you the idea here. This number is that proportionality constant that Stefan measured. So we just call this then Stefan's constant. And so it depends on the whole part of Mother Nature. And so the total power depends upon its temperature, its area, its emissivity, and, did I say that right? And its constant, yeah. Oh.
Yeah. So the power is the power of radiation that this object's emitting, right?
Right.
So if white was 0, doesn't that mean it's not radiating any power?
Exactly. So this shiny thing radiates very little power.
Well, you just said it very little. So, but 0 is 0.
You can never explain your man.
It's not equal. All right. So the 0 and the 1s are these ideal things that never exist. All right. So this black thing is probably 0.95. This real shiny one might be like 0.1. Okay.
Actually, I have a different question.
And so it's a whole scale. Yeah. That was not your question.
No.
Okay.
I thought we were saying that the shiny one was emitting more power.
No, it reflects. It doesn't allow the hot water to emit its energy. Okay, so again, imagine me inside of that container. I'm the hot water. I give off radiation based upon this equation. It goes out and it hits the surface. Then what does it do? In this case, it reflects back in. And so this hot water does not radiate very well. It's a poor radiator of heat. The shiny surface has trapped it back inside. And so it's a kind of a rating. If it makes anything easier, like I said, we're just going to deal with the number one every time we talk about this until we get into chapter 40. Yeah. Stefan's constant is some number I was getting to. Here we go. Times 10 to the minus 8. The units would be watt, would be square meter, and it would be Kelvin to the fourth power. And so that would be the total power. For those of you interested in astronomy, this is a perfect calculation to saying how much energy comes from the sun, how much comes from the stars. We can really easily say, okay, this is the surface temperature of the sun. Our sun's about 5,500 Kelvin, and so we can put that in, raise it to a power of 4. For the sake of discussion, we'll just say it's a perfect radiator, so we'll put a 1 there. We have a good idea of what the radius is, so I can get the surface area, 4 pi r squared, the surface area of a sphere. I can multiply it by Stefan's constant, and I can tell you then the total power being radiated through radiation coming from the surface of the sun.
So would the sun be a 1?
Yeah, so I'll put the sun as a 1. How about 0.999 there? How's that? And it's yeah. So that's this last one. And so again, you probably notice this probably well in the morning time. We talked about you stepping on carpet versus stepping on tile, but maybe you've also noticed it when you got up. Maybe you, I won't say you were naked, but maybe you had very little clothing on and not much covered. But wouldn't your body be radiating? But then wouldn't the walls be radiating? And so you would be absorbing what they're radiating at you, but then you would be losing some by your radiation. So the net radiation between you and the walls, something like this, I'd say power net, would be the hot one losing you and the cold one coming to you. And for simplicity, I'll just say they have the same E value, but this would be temperature of the hot to the fourth power and temperature of the cold one to the fourth power. And so that would be the difference between how much more you are radiating out of your body than is being radiated back into your body. And so you probably felt cold. And if, on the other hand, these were warm walls, which probably didn't happen today, but it could be a hot day where, you stand next to a block wall, you could actually feel more energy coming into your body, and you go, what? It's just kind of warm over here. That block wall has just been in the sunlight for the last 3 hours, and as I stand near it, it just has a higher temperature than the surface of your skin. And if it has a higher temperature than the surface of your skin, it's radiating more. You may not see it with your eyes, but it is radiating more. And so as it radiates more, you would be absorbing more energy than you are giving off. And because of that, it feels warm to stand next to it. Kind of like standing next to a fire. You feel warm next to the fire. It radiates onto you, you radiate outward, but it radiates more than you put back.
So does this kind of have something to do with right when the sun comes up, how the temperature drops a little? At all, or do you notice that?
I guess no, I haven't noticed it. And I know.
Talked about it, I heard somewhere on the internet. So right when the sun comes up, how it drops just this smidgen.
Well, that's the coldest the Earth will be right before the sun comes up. Before you see
Yeah.
the sun. That's it.
Yeah, well, yeah, if that's what you're referring to, that kind of makes sense. Actually, but that might be a good example of radiation cooling is the planet Earth. Did we have clear? Do we have clear skies last night? I don't think we did we? Was it kind of cloudy? But have you ever noticed on clear nights it can get really, really cold? And there's a couple of reasons for that, and one reason is this radiation cooling. Remember, the surface of the Earth, it's been warm during the day. The Earth turns away from the sun. It is now going to radiate that heat out into space. If there's a cloud layer, it would then trap it and reflect it back perhaps, or at least store it in the water moisture in the cloud so it doesn't leave the atmosphere, it doesn't leave our area. And so this last storm we had was actually not really cold. I mean, we got a lot of rain, but what was it, like 57 degrees, 59 degrees? It was not cold, and it did not get cold at night. It stayed about the same temperature. There was no chance for the Earth to cool down. It wasn't radiating. But as soon as the skies go clear, and tonight might be a good example of that, watch tonight, watch tomorrow morning. It can dramatically cool, and the radiation can really then leave the Earth before it, from it. And in fact, the whole idea of global warming is based upon that simple idea. That is, if we fill up the atmosphere with gases that don't let the heat radiate out, well, then we were trapping the heat. And so this carbon dioxide and the methanes that we keep producing are going to trap it in here. Well, I better stop there and move into chapter 21 so we don't end up too far behind. That's more than an hour there. Let me call that quits and let you work on the homework. I was thinking I might have time to do an example or two, but I did the meat of the example, so I'm gonna pass on doing an example so that we can get as much as we can into this next chapter here. And so now that we have our three mechanisms of how energy is transferred, and like I said, this last one we're going to revisit when we get back to chapter 40. Let's keep going in our thermodynamics and go to chapter 21. Finally, your author says, let's look on a microscopic level. And I think I mentioned to you at the beginning, I like to kind of be throwing the microscopic picture out there at the very beginning and saying what's going on a microscopic level, I think helps. And your author's kind of avoided it until now. And now he dives in full throttle. He says, all right, let's take a look at this. And there was an amazing calculation, an amazing discovery that I'm hoping you will see. I will start back with this picture that I think you've got in your mind. If you could get down on a microscopic level and look at the molecules in this room, what would you see? Hopefully what you would see is a bunch of atoms bouncing around. And so this is called the kinetic theory. And so when the kinetic theory was first proposed, some of the early scientists said, well, okay, if what is happening is the movement of atoms, then we should be able to explain all of this thermodynamics in terms of mechanics. And the amazing thing is, you can. And so if you begin to take the world and say, all right, on a macroscopic level, you may view pressure and volume and temperature on a microscopic world. What are all of these things? And probably the best answer I can give you now, which is probably not a surprise because it's the same answer I've been trying to say, is if we look at the molecular motion, we could explain why is there a pressure, why is there a volume, why is there a temperature. And that's section 1 here. And so your author takes a little bit of time, but I think it's good time into doing the following. He says, all right, is a gas really atoms bouncing around? And the calculation we're about to do when it was first done was overwhelmingly one of the best, conclusions that supported the kinetic theory. Because, and I'm not sure which one did it. It's probably Boltzmann or Maxwell or both said, look, here is a box. If you had just these little atoms bouncing around, that should explain why we have pressure. So here's what the author's going to do. He says, imagine a box. And so here's a box. It happens to be a cube. It's got length, width, and depth of d. But imagine just one molecule in here. So it's got a mass of m naught. It's traveling with some velocity. This part is the velocity in the x direction, and so it has a component in the x direction. It may also have a component in the y direction and the z direction, not really focusing so much on that, but just on the x direction. In fact, I think his second picture might be even more helpful here. Imagine this molecule hitting the sidewall. And so here's this molecule. It's, again, got some velocity. That would be made up of a horizontal, an x component, and a vertical component. And as it comes along, it hits the wall and does what? Okay, bounces off. So now look at the velocity. What's the velocity now? Well, it still has the same y component, but what happened to the x component? Yeah, it changed direction. It's equal in magnitude, but opposite in direction. And so again, it was one of these early scientists who said, well, if what you're saying is true, then the pressure is caused by the collision of that molecule. And not just that one, but the whole box filled with molecules. But if we start with just one, we could say, what is the change in momentum in the x direction? And so hopefully what you'll see here in this first little section of this chapter is we can go all the way back to mechanics, and from mechanics we can derive an incredible amount of stuff, and it can explain all of this pressure and volume and temperature stuff we've been dealing with, and it will give us some deeper insight to it. Watch, if I do this, then I would say that this was the momentum before the collision. This is the momentum after the collision. Actually, I guess I should go final minus initial. So after the collision, it has a negative momentum. Before the collision, it has a positive momentum. So when I subtract the two, I get a negative 2 m naught Vx. That's the change in momentum of this object. It's only in the x direction. It took a ricochet off the wall, but it kept its momentum in the y direction. Changed only in the x. Now, the reason I bring that up is because, again, momentum was a discussion we had, chapter 9 of Physics 121. We also saw in Physics 121 that the force was equal to the rate at which momentum changes, right? So if I say, let's just kind of look at the average force. Now, I say average because, again, if I were to draw this atom in here, it may do something like that. And if I were to plot the force as a function of time, I guess it would look something like this. No force, no force, no force, because it's not hitting the wall. And then there would be a huge change in momentum when it hit the wall, huge force on it, kind of like a baseball being hit by a baseball bat. And then there would be nothing, 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 until it hit the next wall. And then when it hit the wall, there'd be a huge force on it. Fair enough? All right. But if I do the average, then I could say how much force is on that wall averaged over time. I mean, obviously there's only a force when you make impact with the wall. And that happens only every time it comes back and ricochets. But here's the neat thing of the math then. If you look then at the average force on the wall, and of course depends which wall we're talking about, but we're just going to do the wall to the right on the x-axis here. The average force then would be the average change in momentum over the time it takes between those collisions. So we just calculated that it's going to be a 2m not Vx, and I'm going to just drop the minus sign and say, look, this is the force on the wall, because that's negative of the force on the particle. So this is the force on the particle, but opposite of that is the force on the wall. But I won't even worry about plus or minus. Just let me just take its magnitude, and then I need to divide it by the time. Well, the time. Wouldn't that be the time between each collision? So there's my delta t. Right? Now again, I want to make sure I got this picture in your mind clear. I am really saying that there is an impact and then nothing and then another impact and then nothing and then another impact and then nothing. But I'm saying that's equivalent to some kind of average. Well, take this down so you guys can see a little bit better. But how much time does it take between impacts? Well, if this thing kind of went back and forth, and this is distance d, doesn't distance equal to velocity in the x direction times time? And so if you're letting this molecule go from the wall here, bounce off and then hit the wall again, then the distance it travels is 2d, isn't it? The velocity is the velocity it has in the x direction. And then there's my delta t. How much time does it take? And so what I can put over here for time is a 2d divided by Vx. All right, so I've got the momentum change, I've got the time. The 2's cancel off, and you end up with m naught, velocity in the x direction squared, over d. And so that would be the average force I would get on that wall. Now that's only for one molecule. Now let's fill the whole thing with a bunch of molecules. What if I had capital N molecules? Well, I guess kind of my average force would be N times that number, because every molecule would kind of be doing the same thing. Now it would be much more complicated, I realize, because some would be hitting the other molecules before they ricochet back. But it would be a more realistic thing of why the average could be useful, because if I only had one in there, then it hits it, then nothing, then it hits it, then nothing, then it hits it, then it's nothing. But what if I have 100 trillion molecules in there? And even that's a small number of molecules. Yeah, there's more molecules in one glass of water than there is glasses of water in all the oceans of the world, by far. And so we never should forget how many molecules there are. There's more molecules in a glass of water than there are grains of sand in the entire oceans and deserts of the world. It's an amazing number of molecules in there. So it kind of makes sense why we can just say, let's not worry about the time in between, because the truth is there's always at one instant lots of molecules making a collision on that wall. Most of them are not. Most of them are somewhere else. But this would be the average force on those molecules. Well, let me keep going here, because these molecules are ricocheting around, and because of that, I did one more thing from here to here. I'm going to put the average speed squared in the x direction. Because if you had a whole box filled with these molecules, wouldn't they sometimes go just straight up and not even in the x direction? And other times in the z direction? And so there's a total mismatch of the velocity. It keeps changing. But fortunately, there's so many of them that I can say that at any given average, they have the same average. I mean, I should say at any moment that they have an average that changes their value changes with time, but there is some kind of average. I'll keep going with this, because if we extend this out a little bit more, you might write it this way: that the velocity in the x direction squared, and the velocity in the y direction squared, and the velocity in the z direction squared is the total velocity of the molecule. Now, it totally keeps changing, I agree. And the only one I'm interested in is the x direction. But I think it's fair to say that the average of the x's and the average of the y's and the average of the z's is probably the same number, right? They're going to just ricochet around. And sometimes they're moving to the x direction, and sometimes they're moving to the y direction, and sometimes they're moving to the z direction. But I could write this then as each of these being equal, at least statistically on average. So 3 times the average of the square in the x direction is the actual average of the total speed of them. And here's why that becomes useful. I can then say the force averaged on that wall then would be n times the mass of that molecule times the velocity squared in the x direction, averaged. Oh, and that's, I guess, what I want to get rid of. And so I write this as 1/3 v squared average, so no x anymore, over d. And so finally, we're getting to the point of this calculation. How would you get pressure on that wall? Well, the pressure would then be this force and then I would divide that by the area. And that area with that d makes this come out to be n m naught v squared average over 3. And this, I hope you can see, is volume, distance cubed, right? The length times the width times the depth. And so be careful here. This v is not the same as that v. This is volume. Actually, maybe I'll even spell it out there. Volume. Okay? But here was my point. If I bring this to the other side of the equation, I then have pressure times volume is equal to, and I'm going to do a little more work here, but it's the number of molecules. In this case, it's 1/3 mass of the molecule, and then the average of the square of the speeds. Lester, you look like you had a question.
Never mind. I divided d squared by the marker.
Right, I divided by the d squared, and so the d's all go together. Yeah. And I get d cubed. I'll take one more step, and then we should have a long discussion here, because as I said, this was the magical key step that really made people believe in the kinetic theory, because it does explain and goes beyond just explaining what we already knew. I'm going to write this as PV equals, and I'm going to write it as a 2/3 N, and then a 1/2 m naught V squared averaged. And so all I did was put a 2 upstairs and a 2 downstairs. And so I didn't really change anything. But this is where I want to stop. I'll even put a box around it here. And so after we just did all of our mechanics, what do we notice? Pressure times volume equals something. And the early scientists already knew PV equals what? Yeah, nRT, or N Boltzmann's constant times T, right? And so this does predict that there is a relationship between pressure and volume. And that's the neat thing about this derivation. If we go back to mechanics, we can derive the ideal gas law. But it gives us some insight also, because not only is there a mathematical connection, and I better put arrowheads over there to make sure you know that, or little lines over there so you know I'm talking about volume, but this could be related to that. If, what? 2/3 N 1/2 m V squared averaged is equal to, nRT, or I'll do NKBT for a moment. Right? That's what it is saying. And in fact, let me go ahead and just write temperature by itself. Because when I do that, I can then write this as 3/KB times 1/2 m V squared average. And the first thing I want you to connect is that this is saying temperature is proportional to what? Kinetic energy. And the whole reason I added a 1/2 factor back here was so that you would see what I was after here, is that this gives us some further insight. We've been saying it from the beginning. Your author didn't. He was waiting for this step. But I've been saying it from the beginning. What is the difference between something hot and something cold? Yeah, it's the motion of those molecules. But did you notice I was a little vague? I said the motion. So when I said motion, was I talking about the speed of the molecules? The kinetic energy of the molecules? The momentum of the molecules? What is temperature related to? And now hopefully these few steps show it to us. What is temperature related to? The kinetic energy. And so when something warms up, those molecules have more kinetic energy. And so be careful here. Not necessarily more speed. Why? Right. Don't the molecules have a different mass? Think about this room for a moment. We've got a bunch of molecules in this room. Some of them are carbon dioxide. Fortunately, some of them are oxygen. Many of them are nitrogen. Some of them are H2O. Aren't they all at the same temperature? Are they all going the same speed? No. So when you say they have the same temperature, what are you saying they have the same as? Kinetic energy. And that's what I want to make clear. If I didn't make it clear before, and I probably didn't, because I just kept doing things like this. Oh, I put it down there. But I kept turning it on and saying, if you warm it up, what happens? Yeah, they go faster. But what I didn't really emphasize is temperature is not related to speed. Temperature is related to kinetic energy. Now, granted, kinetic energy is related to speed, but it is also related to mass. And in fact, that's why your author pauses here and he says, let's take a look at the motion of the molecules in this room. I think it's table 1 where he lists these. Yeah, he says, okay, let's look at some different molecules here. For example, in this room, there's quite a bit of carbon dioxide. Does he say room temperature somewhere? Oh, 20 degrees, okay. But there's a lot of carbon dioxide. How much does a carbon dioxide molecule weigh? Well, 44 grams per mole, which maybe I should pause there. How do I know that if it wasn't listed here? Yeah, and for some of you who haven't worked with the periodic table, let me show you something real basic. They list these out. The carbon is a 12. There's the carbon, so there's a 12. There's an oxygen, it's a 16. And so you've got 2 of these, that makes 32. Added to the 12, that makes 44. So carbon dioxide is actually one of the heavier molecules in this room. It is 44 grams per mole. How much does oxygen weigh? 32. How much does nitrogen weigh? 28. Again, you can look up there. They're each 14. And the other one, water. How much does water weigh? 18. So I'll say it again. Do they all have the same weight? Do they all have the same velocity? Do they all have the same temperature? All right, so I would say in this room that all this mixture, they all have the same temperature. And what I want to emphasize is when I say they have the same temperature, what does temperature equal? Maybe I should put a box around it. Temperature is equal to what? It's related to what? The kinetic energy. And so in this room right now, the water, the nitrogen, the oxygen, the carbon dioxide, I'd say they all have the same temperature. They all have the same kinetic energy. And therefore, they have different speeds. Which one would have the slowest speed? The heaviest, which would be? CO2. So there it is. It's a little heavier. It's traveling only 408 meters per second. Oxygen, being a little lighter, to have the same kinetic energy, is going a little bit faster. Nitrogen, being a little lighter still, it's got to go a little faster. And then finally water, quite a bit faster by the time we compare the slowest, carbon dioxide, with the water. And so again, I'll camp here for a moment to emphasize this is an important derivation from the idea of our mechanics. And so our mechanics and our thermodynamics become one and the same. We can start with the motion, we can do forces, and we can work out what is going on. And what we learn by that is we learn that temperature is related to kinetic energy. I think this makes a good experiment here. I have a tube. Now right now this tube has lots of air inside. I've got a valve and I'll open it up and there's a bunch of air. That means there is water in here. There is carbon dioxide. There is nitrogen. There is oxygen. Let me use the vacuum pump here and remove the air molecules. And so now there is hopefully very little to no molecules in there. I'll close the valve so molecules can't get back in. And so right now I've got an empty tube, no molecules. I'll pull this cork off. If I pull this cork off, what's going to happen? They're going to go rushing in. I mean, look how fast they're moving, right? That's 20 degrees. We're leaving a little warmer than that one. Which ones are moving the fastest?
Water.
Water. So which ones, as they go racing in, are going to go down here?
Water.
The fastest. The water. The water will get here first. And so of all these molecules in the room here, the water one should get here. In fact, you will hopefully see as the water ones come in here, there'll be so many water molecules in here that they will condense and you'll get a little bit of moisture. Now, not much. It's not like there's going to be a glass of water down here. Okay. But it will get a little foggy on the surface as we get condensation. And so I'll pull it off. And so sure enough, there is the H2O molecules, the ones that are traveling.
You have to do that to get a glass of water.
Might take a while, but if it doesn't rain enough, we might be doing that a lot, right? Squeezing some water out of the air on a regular basis there. So that is what I would call step number one, if you will. This is the neat thing about this calculation. It gives me, like I said, some more insight. And so let me be a little more clear from here forward. When I ask this question, what's the difference between something hot and something cold? The hot one has more kinetic energy. It's not just more motion. It's not just more speed. It's more kinetic energy. And so that's where that little proof comes from. Well, again, let me keep going here because I use this as an opportunity to show you that the temperature is related to kinetic energy, but I also indirectly used it as an opportunity to ask this question, where did these numbers even come from? Or put another way, couldn't you use this relationship to tell me the speed based upon temperature? And so let's give that a try. Let's rearrange this equation. Let me write the 3 kBT together. So I'll put this over to here. I'll go ahead and cancel off the 2 and the 1/2. I'll even divide by the mass of the molecule, and that should be equal to the average of the square of the speed. If I take the square root of both sides, I have the square root of the average of the squares. And on this side, I have the square root of 3 kBT over the mass. Now again, let me make this real clear. What I was trying to show you is that wouldn't different masses come out with different speeds? But also different temperatures would be different speeds. That's why, again, in this chart, the author is trying to say, these are the speeds of the molecules, but this is at 20 degrees. Because if it was more than 20 degrees, then they would have more speed. This we often refer to as the RMS speed. And if you haven't heard that phrase, let's take a moment and talk about RMS, because what's really meant here can be a little confusing. What do we mean by RMS? Well, it stands for root mean squared, and you can kind of see it, right? What am I doing? Well, I guess I'm taking the speeds and I'm squaring them. Then I averaged them. That's what I meant by average. And then I took the square root. Because we never do it that way, right? You would have your numbers, And the first thing you would do is square them, so you'd apply the operator. Then you would average them, you would apply that operator, and then you would take the root, you would do that operation. So it's this, then gets this, then gets that, right? It's a composite function. Anyways, but that's the typical notation in math. All right, but not worrying about the order, but that's the kind of order we do for composite functions. So we call it root mean squared, not square. Right. So not like we're reading left to right. It's more like we're doing math right to left. Okay. Yeah. But good point. All right. But anyway, that's why we call it here. But I want to be real clear here. What is this number? Is this the same as the average speed? Is the square root of the squares averaged the same as the average of the speeds? Same as the absolute value? No. And it's so easy to think that. Let's pause and take a little bit of a break and look at some math. Now, not much, because we don't have much time here, but let me give you some numbers here. What if, and I wrote a set of numbers here to kind of illustrate this point, what if I had these numbers? A 2, a 3, a 3, a 4, and a 5. And I'll just say these are the speeds of the molecules. Whatever units, in hundreds of meters per second or something. But if I reached into a box and I said one molecule has a speed of 2, another has a speed of 3, another has a speed of 3, another has a speed of 4, and another one has a speed of 5, what would be the average speed? Well, wouldn't I go 2 plus 3 plus 3 plus 4 plus 5? And then divide it by 5? And if I did my math right earlier, I got an average speed of 3.4. What is squaring them, then averaging them, and then take this square root? Do I get the same value? Well, let's give it a try. 2 squared plus 3 squared plus 3 squared plus 4 squared plus 5 squared, all divided by 5. All then taking the square root, right? So I square everything. Then I take the average of all those squares. Then I take the square root. I get 3.55. So again, it's worth asking ourselves, is the RMS the same as the average speed? No, no. It is the average of the squares. It's the square root of the average of the squares. And so these are slightly different numbers. So be real careful here that we do not mean this. And so I should put no. No, 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 no. Right? These are different things. In fact, I'll even do you one more. I'll put the most probable. What do I mean by most probable? That means if I reached into a box and grabbed one out, what is the most likely speed I would get? 3, right? There's 5 of them. There's a 2 in 5 chance that I would grab one that had a speed of 3. There's only a 1 in 5 chance that it has a 5, a 1 in 5 chance that it has a 4, and a 1 in 5 chance that I grab a 2. But there's a 2 in 5 chance that they have a 3. So the most probable speed would be a 3. The average speed would be 3.4. And the RMS speed would be something yet different. And so be careful with these numbers. They mean something different. They are not quite the same thing. And that's what I wanted to illustrate with those numbers. And so this is giving us the RMS. The RMS is a great number because when you square it and multiply by its mass, then you're getting the average kinetic energy. That's why we care about the RMS. It's not because we don't want to know the average speed. We usually don't want to know about the average speed. If we want to know the average speed, we would then calculate it. We would call it V average. But V RMS is something that would be very useful if we took that number and squared it, and we wanted to know the average of that. And for those of you who took electronics with me, notice we did the same thing in our circuits, and the rest of you will do that next semester. We will talk about the average of the squares. That can often be more valuable than the average of the speed. And this is just one of many examples, but for many of you, this is the first time you've come across an example like this. And so, again, RMS is not the same as the average speed. It's not even the most probable speed. It is what would be important if I wanted to know the average kinetic energy. That's where it becomes important. All right, well, let me do a third thing, because there's three very important things you're seeing in this equation that I have now erased. Maybe I should put it back on the board here. But the third thing buried in here was pressure times volume equals 2/3 N 1/2 m naught V squared average. I think that's what we had. Is that right? Yeah. Let me set that equal then to this N kBT like we had. And look at this for a moment. If I cross out the N on both sides and leave the kinetic energy here, so there's the kinetic energy. I still have 1/3 there. I'll bring that over to here. I'll go back a step. And what I mean by back a step is, didn't we say that 1/3 of the average square of the speeds is equal to the RMS speed in the x direction? So let me put that together. And there is a pattern that you will begin to see. This is the first time you've seen it. So of course you're not going to recognize it as a pattern quite yet. But this 1/2 kBT is equal to what? It's not the whole kinetic energy, right? It's really 1/3 of it, right? It is a kinetic energy associated with just the x motion. But I would go one further. Wouldn't we also say that on average anyways, whatever velocity it had in the x direction, it also has in the y direction? And also has in the z direction? And the fancy word we like to say here is this molecule has freedom to move in 3 dimensions. We call it 3 degrees of freedom. It can move x, it can move y, and it can move z. And so the motion of this molecule, whether it moves x, y, and z, we can't control. That's just a statistical randomness of these molecules bouncing around. But they have the same number, and that equals to this 1/2 kBT. And so this 1/2 kBT equals the energy for 1, and I'll use a fancy word here, degree of freedom. And so we have different places that the energy can go, and in this case it is 3. This we are going to see a lot, starting in this chapter and continuing in the next. That if the molecule can do something, say move in the x direction, how much energy does it have in the x direction? 1/2 kBt. The same in the y, same in the z. But here's where it can get kind of fun. What if the molecule is more than our simple model? Here's our model. This molecule can only move x, y, and z. What if I had a little more complicated molecule? What could this do? It could move x, y, z, and spin. And not only could it spin around this axis, excuse me, which you might call a z-axis, what else could it do? It could spin around this axis. Now, I suppose you might say it could spin around this axis, but we'll kind of ignore that one only because didn't we learn that the energy is related to the moment of inertia? And didn't we learn that the further something out, the more moment of inertia it has? So the truth is something spinning like a hot dog doesn't have anything like spinning this way. So I'll ignore this one for a moment and say this molecule is more complex. How many degrees of freedom? How many different kinds of energies can it have? It's 5, right? It can translate x, y, z, and it can rotate y and z. And I'm ignoring the x. A more complicated molecule could do what? Could move x and could move y. Could move z. Could rotate y. Rotate x. Rotate z. It could flap in a plane. It could flap in another plane, and it could have a lot more degrees of freedom. Now, forgetting the flapping part, I would then say this has 6 degrees of freedom, 3 of translation, 3 of rotation, and ignoring any flapping, I can then count those in there. And we're going to do that because where does the energy go? If you just throw in a bunch of energy to the molecules, can control where it goes? Does it only go in the x direction? No, if you started them all in the x direction, what would happen after that? You took a bunch of molecules and only let them go in the x direction, but once you let them go and they hit the walls, what happens? Then they evenly distribute and you get this much energy in every degree of freedom. And so when it comes to calculating the temperature and the energy of our system, we need to know how many different places the energy can go. If it can only go to translation, then we only got 3, x, y, and z. But if it is something that is shaped like this, then the energy can go to 5 degrees of 5 degrees of freedom. If it is something shaped like this, it has 6 degrees if we don't count any flapping. If we start doing the flapping, it's going to get ugly. And so we won't at this level, but we will get started with that and we'll start looking at our other options. Question? Did you still have a question? No. Okay. Anyways, I wanted to make sure I covered this because that is something neat to have. Well, bummer. My time is very limited. But here's where I wanted to take advantage of that idea. Let's come back over here and heat something. And so now that we hopefully have a deeper understanding what if I take this gas that is made of all these bouncing molecules and I warm it? And you guys might remember from the lab, this is about 80 degrees. So I'm going to warm up that gas to 80 degrees. Okay, so I put it in here. It may take a while, but eventually this will warm to 80 degrees. Fair enough? Let me do it slightly different. Let me cool it back down for starters. So that's about room temperature, right? Right about there? Okay. Before I warm it this time, I'm going to clamp it. I'm going to warm it to 80 degrees again. Unfortunately, there's nothing to watch go up or down here, but both times I warmed it to 80 degrees. Fair enough? Did it take the same amount of energy? Last chapter we said this was real important. Wasn't it path dependent? The amount of energy we add to a system depends how it warmed up. The first time I did it, how did I warm it up? Constant pressure. What do we call that? Isobaric. The second time when I warmed it to 80, what do we call it? Isovolumetric. Would it take the same amount of energy? Oh, some of you are uncertain.
That one doesn't take.
The answer is no. Why? Which one would take more?
Isobaric.
Why would the isobaric? I heard somebody say isobaric would take more. I agree. Why?
Because isovolumetric, the work is zero.
Right. You see, when I go to warm it like this, at a constant volume, isovolumetric, when I add energy, all that energy makes the molecules go faster. It gives it all to the kinetic energy. That's where it goes, and it warms it up. But on the other hand, if I cool it back down and warm it up with a constant pressure, even though I'm still warming it to 80 degrees, I claim that would take more energy. Why? Because as I give it energy into my gas, where does some of that energy go? Work into it. Let me draw our diagram again. As I send heat energy in, if it's isovolumetric, all that energy makes the molecules go faster. That's the easy case. But if it's isobaric, what happens? Yeah, then, whoops, this would be work. Some work comes out. And so the amount of Q that has to go in has to be enough to not only warm these molecules up to 80 degrees and make them move faster, but some of that energy coming in then leaves the system by it doing work as it expands. And so, as we said last chapter, and we're out of time here for today, shouldn't there be a different specific heat needed to calculate how much energy does it take to warm it up when it's isovolumetric versus isobaric? It takes a different amount of energy. And fortunately, the work that we just did right here with the degrees of freedom will help us calculate that. We'll stop here for today, but we'll be able to calculate those on Thursday and begin to see it is a different number. And there's an important difference about those numbers.